Well, good morning, everyone, and welcome to the Art and Architecture Shop. Art and Architecture. Half this place is owned by Stamps School of Art and Design, and the other half by Taubman College of Architecture and Urban Planning. We service a lot of people here. So some of what I'll talk to you about today, of course, is going to be the essentials of safety in an old technology environment, but also a lot of the information that'll get passed along to you either today or by reading through the Woodshop orientation that will be, I think it actually already is on the Stamps website, and will probably be included in part of your orientation packages at the beginning of the term here. Will be how to manage your activities and plan your work when in a place that can be very busy. Now, obviously, this coming semester, we are never going to be as crowded as we would normally be. COVID is putting certain dictates upon us as to how many people we let in the door and how you're going to behave when you're in here, and social distancing and face covering and all that business. And maybe we'll talk a little more about that before this is done. But it would suffice to say that that's not going to last forever. And with any kind of luck, we'll be back to normal, which means this place can be a zoo. So some of the information I pass on during orientation has to do, once again, with how you're going to plan your work and access us and effectively use equipment not only safely but productively. So old technology, you don't listen to or hear many people talking about old technology in a positive light nowadays. Matter of fact, everything has to be faster than it was 5 minutes ago, and have more memory and storage and capacity and all sorts of stuff. And old technology operates on some very different sorts of premises, and perhaps one of the things that folks have to really work at when they come into a place like this nowadays is making that adjustment between the technological environment they're immersed in most of the time and what an old tech environment is about. I just use that word again, old tech. Whether you realize it or not, when you cross our threshold, you go through a time portal into the 19th century. And in the 19th century, there was lots of software, probably quite a bit more than there is today, but it was all here. There's nothing about old technology that will anticipate you, that'll think for you, that'll work things out ahead of time. You're accountable for every little thing that goes on. And so it is a mind shift when you start working with this stuff. Also, faster is not always better. And like all technologies, you only get good at them when you acquire the skills and knowledge and experience to use them well. But with old technology, there's other stuff going on than just your cognitive engagement. There's muscle memory to develop as well. A lot of this stuff is kinesthetic sport. You're going to gain physical, muscular skills, not big muscles, but you're going to conduct yourself in a particular physical way around machine tools in order to make them work well for you, but also to do things safely. So there's going to be a bunch of things that I'm going to try and tweak your imagination about to recognize where there are disconnects and why. And you'll find your own examples in your own life as time moves on and you engage this stuff through your career here at the University of Michigan. It's suffice to say we have machinery and tools and equipment and processes available to you here that are extremely powerful. They can affect your ability to take all manner of creative idea and get it into three-dimensional reality. But once again, there's going to be skills to develop. I'm going to spend a little time referencing this Woodshop orientation outline, and then start to elaborate on some of this as we go. If you look at the very first page, and I'm guessing once again that this is part of your orientation package, or certainly will be before you get here. Under general policies, suggests that we're very much as a lab would be in any other curriculum around the university. We're here to satisfy your assigned duties in your various classes. That's our primary reason for being here. And yes, during this COVID time where we're limited to the number of people we can have in the space, and it's going to have to be scheduled and so on in order to control occupancy, it's probably going to be most specifically assigned work. We're still talking about how to create a kind of free swim situation in the evenings that's not necessarily your class time to be here, and I think that'll be happening probably through Stamps collaborating with Tubman to give you some sort of token that will allow you in the door for a period of time on evening hours. But we haven't ironed all that out yet, but I'm confident we're going to do something, because everybody needs a little more time than just what they get in class to get work done. We reserve the right to control the kinds of materials you get to work with in here. Usually common sense, but maybe not always. Art, design, architecture are all material intensive sports. We would like to immerse ourselves in every new material that comes down the pike, and that's a good thing. That's adding to our creative vocabulary. But we have to exercise a little bit of common sense. We will facilitate all manner of plaster and concrete work, but we don't handle plaster and concrete in the shop. That's a machine shop contaminant, damages machinery. We'll help you make the forms and tools and things that you can then go out in the driveway and do the messy side of the task. That's just one example. There are some materials that would just never come into a wood shop or any kind of shop. And I say wood shop, but we also do metals and plastics in here. Things that are going to damage machinery, or things that are going to present a health hazard. We're not going to machine, grind, cut treated lumber materials that are treated with either insect and fungus resistant chemistry or fire retardant. Those things are just dandy to work outdoors the way they're designed to be worked, where the byproducts dissipate into the environment in a below hazard level. But when you come into a shop environment where all that stuff gets captured in the machinery and our dust collection system and so on, that can produce quite a problem. So if you have any uncertainty about a material you're going to acquire for a project, talk to us. Send me an email. We can maybe even set up a time to meet. Usually I don't have to say that, but this semester is perhaps going to be that way. Not only will that advantage you in learning what you can or can't use in here, but usually we've got a pretty good idea who's giving us the best deal on materials, because we buy thousands and thousands and thousands of dollars of materials every year with all of our students. I mean, we're covering almost 1,500 people here at Stamps and Tubman. So there's a lot of good reasons to stop and talk to us about materials before you procure them. We reserve the right to boot anybody out as misbehaving. Now, that's what I call a police clause. We almost never have to use it, and we never like to use it. But it suffices to say, when you're working in here with other people, you have to be considerate of everyone around you. Not only do you have to be operating safely, but you have to be operating in a socially acceptable way. And it's for the one person out of 1,000 that might have to have that said that I bring it up here. And I know most of you, it's not going to be an issue. I'm quite certain now, with what we've been going through over the last, by the time you get here, almost 6 months, that the behavior's already started to pattern itself with all of you about keeping your social distance and your face coverings and those kinds of things. So that'll be added to the mix of being good citizens in the shop along with everywhere else. And last item under general policies is about storage. We service more people than any other single facility in the building, so it's suffice to say we don't have any room for storage, not reasonably. The rule in here is 1 week. Any material that comes in, hasn't been worked on, handled, manipulated in a week's time, we'll assume has been abandoned. We'll either throw it away or put it in a scrap. We're not mean about it. You have some special reason you couldn't get here, give us a call, drop me an email, do everything we can to help you out. But don't plan on using this as a storage facility. It's also not a campground. We're a service entity. plan your work well. You're going to come in and prepare things, then take them back to the studio to put stuff together. But you're not going to store work or materials here unless you're working on them consistently. And again, if you had any large amount of material to bring in the door, you'd have to let us know to even have it received here. So again, we've got a lot of folks to cover, and so plan on talking to us throughout the semester. Shop hours you'll see on this handout, they may be similar to this coming up. Obviously, most of you have already heard that we're starting August 31st and we're knocking off November 20th. And that'll be the end of the semester, and then the winter term starts midway into January instead of the usual right after New Year's. So there'll be some things that are a little different, and you've probably heard a lot of folks talk about these times as being very fungible, constantly changing. So you'll be paying attention to the postings and signage and things that'll go out on email from the university and your particular program as time marches on. If anything changes, I'm sure you'll be know about it as soon as the rest of us do. Last paragraph on this first page of the orientation is woodshop safety. I'll just go through it with you. Usually we have a little interaction with the group, but that's not happening with this particular approach this semester. So first item says, you know, we're the same as any other program in the university. The more you know, the further you go. And everything that happens in here is going to depend on you investing some time to learn about the processes, the materials you want to work with, to develop skills. And those skills won't necessarily come as quickly as digital skills for you. Again, because there's an extra order of muscle programming, not just cognitive engagement with the stuff you're going to be doing here. So plan on being patient. Patience is a virtue in the shop and with old technology. Patience is hard to be found in the digital realm. If something's a little too slow, it's time to get another app. Time to update your software. Update the software? Sure, but remember, you're the software. So updating that software means you're going to invest more time and patience to get better at it. This shop orientation is really just an exposure to what's going on. And again, this video is really only the first part of what we typically do in an orientation. The specifics of machine operations that I address a whole lot more of than we can do in this video, that moves this whole process up to several hours. What we're going to be doing this semester is assignment by assignment as you have different processes needed by you and your classmates for a particular project. We'll spend 20 minutes at the beginning of that assignment or whatever it is to help you develop certain skills with the machines and the materials you're going to want to work with. But this is just a beginning. It's not a certification process, and you need to know that. What I try to do in our regular 3-hour orientation is get you to the point where you're perhaps a little better equipped to ask questions, because if nothing else, you should become good at framing what your particular creative issues are that require the shop, and learning how to ask questions. We never get down on anyone for asking a question. We will if you don't ask a question and do something foolish. So, and again, most of what's going on here isn't as available as you might think online. What's out there online with these kinds of processes really are predicated on you already having a certain basic skill set, and for many of you, you're not there yet. So you're going to want to talk to us, and we're going to do our very best to bring you up to speed as quickly as possible. In the shop, safety is always going to be our very first priority, as it is in a lot of lab operations around the university, and that is very much a state of mind. It is a way of thinking about things. It is a way of becoming more aware of yourself physically in relationship to things that move and cut and shape and so on, which are part of our machines. it's going to be important that you recognize simple fundamental principles about how and why this stuff does what it does. And you need to realize that this was designed in a time in our history when that kind of fundamental awareness about the physical world was very intuitive, much more intuitive than today, because we have our technologies today take us out of that equation more often than not. We're less engaged in decision making about how we maneuver and navigate the physical world than we ever used to be. So we're going to be pulling you back into an earlier time when you come down here. And your state of mind about safety is going to be critical. Accidents don't just happen. 999 times out of 1,000, when there is an accident, the first thing that comes out of somebody's mouth is, oh golly, if I had only something, which typically means you weren't thinking well enough about it ahead of time. And again, checking your thinking with us is going to help you grow more quickly, become good at this stuff. We're in the business of trying to get you good at using this kind of equipment. We're not here to slow you down, but you do have to talk to us. And after you read through this whole thing and watch this video, write down your questions. You'll probably have some. And next time you see us, we'll address those. So the next page in our little orientation here is general safety. These are just some simple starting principles about safety in here that really apply to almost any physical lab environment where machinery is involved, but labs in general. Number one is we expect everyone to conduct themselves in a mature and courteous fashion. It helps not only you, but everybody around you. You need to understand that everyone's running on the same stress cycle. Midterms happen at the same time every semester. Due dates are often coinciding in several courses. If you're stressed out, people around you are stressed out. Be kind. If you need to jump up and down and yell and scream, well, you probably should, but go outside and do it. Don't do it in the shop where you might startle someone and have them get tangled up in a piece of equipment. So be kind to your neighbors. Eye protection. Well, art and design and architecture are all visually intensive sports. You lose your eyes, well, I hope you're good at music. It would suffice to say that any piece of machinery that cuts or abrades material can and does make a certain amount of that stuff airborne from very fine particulates that can get behind contact lenses and aggravate your eyes to great big things that can take an eye out. We do provide face shields and goggles and safety glasses and so on. And something that's a little different this semester, we do have bins underneath where these things are located. After you've used them, drop them in that bin, because we'll then take and dip them in a solution of Clorox and hang them up before the next person uses them. We never used to do that stuff. And oh, by the way, generally our supply stores, assuming they're open in some fashion or another this semester, do sell safety glasses, and I'd encourage everyone to buy their own. They're not very expensive. You'll always know who wore them last, and you're going to use them other places in here. So that's a good, just generally a good thing to do. I don't know if the art school is doing toolkits this semester. They usually do, and if that's happening, you folks will have safety glasses in that toolkit. Loose appendages. Number one cause of really serious shop accident is you not knowing where your edges are. Anything that's attached to you, whether it has nerve endings or not, is fair game for a moving piece of machinery. Long hair, loose clothing, dangling jewelry, look yourself over, take inventory, take it off, put it in your pocket, tie back your hair, tuck your shirt tails in. Don't wear aprons down here. They might make good do-it-yourself video stuff, but it's foolish in a real shop, because all of our dust pickups are usually down below tables where apron tails can get sucked into machines. So you want to leave your aprons up in printmaking or other places where they're more appropriate. Closed-toed shoes. I have nothing against sandals, but you don't want to wear them in the shop. That is an area where you can end up with quite a penalty from OSHA, and then we end up with one as well. If you come in without shoes, wearing sandals, well, we do have to ask you to leave. So if you like to wear sandals, that's cool. Keep a pair of shoes in your locker if you think you're going to be doing shop work. And last item, I've already said it several times and I'll continue to say it. Please don't be afraid to ask questions. We don't bite. There might be some urban legends around that suggest we do, but we don't. We're here to help you out. So don't be bashful. Don't first go on your phone to try and find the answer. We'll have the answer to your specific problem because we've been doing this for so many years. We know what's being asked of you from your faculty people and your course structures, and we can usually get you where you want to go very quickly, but you have to make the effort to talk to us. Well, that's the first part of our orientation outline. Please read through the rest of it. It will give you little hints about the things that go on with our different machines. I'm going to talk about a couple of simple principles now, using a bandsaw to hopefully cue you up for the kinds of things that are common from machine to machine to machine. Gives you an idea how to assess what your role is in operating with a machine tool, as well as cueing you to some of the things that you wouldn't expect. Some things that are commonplace in old technology, but very foreign in our environment today, so that you don't automatically recognize that something's going to act in a particular way. So again, it's part of the mind shift that is going to be important for you to engage. All right, folks, so I'm going to talk a little bit about a bandsaw, not so much for the specifics of the bandsaw, although we'll get into that. I don't know how I'd talk about a bandsaw without getting into that. But to illustrate some of the kinds of thinking processes that are going to be important to you when you're assessing how to behave with a machine tool. This is called a bandsaw, and it gets its name from the fact that the blade is a continuous band. It goes around two large wheels. There's another one on the bottom, the same as this. The blade's connected all the way around. It's almost 15 foot. It's a 20-inch bandsaw. Well, that 20 inch is the diameter of the wheel, and I know you don't care a whole lot about that, but it's going to tell you how much room you have in here to work. Notice how big and heavy these wheels look. That's going to be an important thing to understand when we start using the machine as to how it behaves. So before we can use a bandsaw, we have to have access to the blade, and in order to do that, we're going to have to raise this column. It's both a guard and a guide. And to do so, we're going to have to unlock that column. It's a little knob on the back of the column, and then there's a wheel attached to it. And we're going to lift it so we can get our material in there. Now, because that blade is a continuous band, let me pull this up a ways so that you can see that blade just a little bit. It has some flexibility to it. That's a good thing because it can bend around those wheels. It's not such a good thing if you don't support it close to your work, because the blade can go any number of places other than where you want it to go, the more exposure of blade you have. If you look closely at this column, there's some ball bearings that pinch the side of the blade, and underneath the table there's another pair of guides just like that. The closer this is to your work, the more predictable your cut will be, because it's diminishing the capacity for that blade to bend and twist and move in a path other than the one you're trying to create. So get that close to your work. Typically we say about a finger's thickness. And of course, because we're working around that blade with our hands right now, the machine's at a dead stop. Now, it's important to recognize that turned off and a dead stop are not necessarily the same thing. This is one of those points of disconnect in contemporary awareness about old technology. We're terribly accustomed to having things instantly on or instantly off when we push a button. Now watch what's going to happen here. It's powered up, cuts beautifully. I just turned the machine off. Look at that. Remember those great big large wheels? One on the top, one on the bottom? They're heavy. They act like flywheels. What does a flywheel do? A flywheel stores energy. Now, in the 19th century, you'd walk past a bunch of them on your way to school in the morning, because every little mill, every little shop, every little business that had a line shaft running tools and equipment and weaving things and all kinds of stuff had big flywheels on them. You sit on top of one every time you drive somewhere because there's one between the engine and transmission of your vehicle, but you don't see it and you're not aware of it. Would you believe the number of serious hand trauma in emergency rooms coast to coast have gone up on a curve almost identical to the adoption of digital technology in our culture over the last 25, 30 years? Because people expect you turn it off, it's off. So there is this tendency to get tangled up with something after you've turned it off. Be aware, blade's got to be at a dead stop. Now what I was just doing is called ripping. There's two fundamentally different types of cutting on any saw. One's called ripping. In the case of woodwork, that's cutting parallel to the grain. It also means cutting parallel to the longest dimension. And this particular guide is very good for that. It's called a rip fence. It's terrible to try and do this with, because you don't have enough material on the fence. That'd be an entirely different type of guide, cross-cutting guide or miter gauge. Now, that seems to be something that students have a very difficult time with nowadays. Recognize the difference between a long cut and a short cut and what's the best guide for it. It's very easy to break a blade and to get into trouble trying to use this guide in this fashion. Other thing bandsaws are nicely suited for, other than just cross-cutting and ripping, are cutting curves. That's something we can't do with other saws. There are some limits. It's predicated on the size of the blade and the size of the saw cut or kerf that it makes. All of our large machines, 20-inch machines, all have half-inch blades, and the half-inch dimension applies to the distance between the front of the teeth and the back of the blade. All of our blades, bandsaw blades in the shop, will deliver a 1/16 of an inch saw cut, or kerf in saw terminology. A half-inch blade in a 1/16 inch saw kerf will allow you to go down to a 2-inch radius on a continuous cut. That's the limit on a continuous cut. In fact, when you understand where the limit comes from, we can go down to a 1/16 of an inch radius with this great big saw blade. But this is one of those occasions where you have to understand a little bit about how and why the machine works. Again, folks, this is an example of a kind of thinking process that you can find yourself engaging with almost any piece of machinery or tool in order to get the most out of it. The other thing you need to recognize is to cut anything, you have to push it forward in the blade. Notice all the teeth are on the front of the blade. The operator stands always on this side of the machine where the on-off switch is and so on. You can only cut when you're pushing forward. It's human nature to push right and left if you get off track on a curvilinear cut, and that just doesn't work. It's going to damage the blade, and if you work at it hard enough, start a fire, you know. You're always going to push forward, but you're rotating while you're pushing forward. Good way to think about it, let's say you're making a circular cut. There's going to be a point on your material that would be the center of the circle that stays in the same location on the table. You're rotating, but you're pushing forward. Something very simple you have to understand in order to cut a curve on a bandsaw. I'll cut a couple of curves for you, one that's within limits, one that's not within limits, and then we'll scribble on the board for a minute and hopefully give a little more structure to what I'm showing you so you understand it perhaps a little more thoroughly. So the first one will be a gentle cut well within the limiting 2-inch radius. The next one will be one where I try to push it harder than what it's willing to do, and I'd like you to notice what the difference is between the two behaviors. First one. Makes a really nice cut. It's It's easy, simple. You didn't hear anything bad going on. That make anybody feel bad? Kind of raise the hair on the back of your neck just a little bit. I hope so, because what I was just doing there was not very nice to the saw. Here's the first cut. Nice, clear, undamaged material. Here's the second one. You're starting to see burn marks on your material. It's getting hot. Heat's a problem in almost all machining processes. We work very hard at the design of our tools and the way we apply them to keep temperature down below a certain point. When we get to some machines for working on metals, we actually add coolant to the mix to keep that temperature down, because in almost all machining, heat is an enemy. It's going to damage things. To understand a little better what just went on here, and then ultimately how to, in fact, get much tighter radius, I'm going to have to scribble on the board for a moment here. To understand a little bit better where the limiting radius of cut comes from on a bandsaw, I'm going to scribble on the board for a moment, hopefully give you a little more insight. And again, this is how you learn how to navigate and get more bang for your buck out of a machine, by understanding where the limits come from, because it allows us to re-engineer process. The manual says this is the tightest curve you can make, period. I'm going to show you how you can do all sorts of crazy shaped things with the bandsaw, but you need to understand where the limit comes from. So if we were to take a look at our bandsaw blade in a side view, it might look something like this. And folks, I don't draw to scale, so you're just going to have to take my word that that's 3 teeth per inch, and this is going to be a 1/2 inch because we're talking about a 1/2 inch blade. If we look at it a little more closely from a front view, we're going to see this narrow strip of metal with teeth at that increment that I didn't draw very well. But if you look at it more carefully, you're going to see that the teeth are not one over another at all. In fact, those teeth are bent. They're hooked right and left. And in saw vocabulary, that bent characteristic to your saw teeth is called set. Every saw blade has to be set. In our case, when this saw starts to run, moving down this way, the saw cut or kerf that it makes, and once again, this is not to scale, it's going to be a 1/16 of an inch. The saw blade material itself, well, that's only 25 thousandths of an inch. And you know, I don't care if you remember those numbers. 1/16 is 0.62. What I like everyone to recognize is that one is 2.5 times the other, and that's critical. There's got to be room for that blade to move and to remove the cut material. It's got to have breathing space. If you're to look at your block of material in a plan view, we're looking straight down on our block of material, and we introduce a saw kerf. And for illustration's sake, we'll put a section of that saw blade in there. Can you imagine it can turn right and left just so much before it's rubbing on something other than a tooth? Guess what? That's our limiting radius of cut, is how much that 1/2 inch plate can tangent. With a 1/2 inch blade, that's good to a 2 inch radius. With a 1/4 inch blade, that's good to a 1 inch radius. And we do have one 14 inch bandsaw with a 1/4 inch blade on it. So if all of a sudden this saw kerf were to get larger, what do you suppose happens to our limiting radius? It's going to get smaller, right? The more room I have to turn, the more I could turn in my not to scale drawing. I could turn at a right angle. So I can get quite a bit tighter if I make more room. And the reverse, that saw kerf were to shrink, we could turn less and less and less and less. And how do you suppose the saw kerf shrinks? It kind of showed you when I was over cranking that blade. I got the blade hot. You need to recognize that this bent characteristic to those teeth can only be there by the temperament of that saw blade, the way it was heat treated, the way it was tempered, became hard and springy. Difference between spring and a paper clip, same steel, but the tempered steel is springy. So our saw blades are tempered. It keeps them harder and keeps their shape a little better over time. But if we get it hot, we can take the temperament out of the blade. And in doing so, the blade's going to flatten out and our kerf is going to get smaller and smaller and smaller. See, we're going to expect you to draw on your material if you're going to do curvilinear cutting, because that drawing process gives you an extra point of confirmation as to whether or not you fit what we have here, or if you're going to have to find another way to get there. And there is another way to get there, I promised you that. And it's called relief cutting. Providing relief to the saw blade. And it has to do with this business here. Making more space. Not a big stretch. How do you make more space? Well, I'd simply back out of my cut, come along and cut right next to it. Making more room to make my curve. Lots of different types of relief cutting. Comes from recognizing why the limit is there on the blade. It's how much space it has. Well, the simplest type would be tangent cutting. Not even having to make more space. We're just taking lesser curves to make tighter curves. Another type of relief cutting, take a series of cuts up to your destination cut, just in and out, assuming this curve is a little bit too tight. And what those are going to do is not make a parallel larger saw curve. They're going to create a saw curve that looks like this. Because as you're getting to the point where you'd start to turn too hard, you approach a relief cut and the material is going to simply hinge away from the saw blade. If you can only go down to a certain limit in a curve, you certainly can't turn hard inside corners. But if you can bring straight lines tangent to a curve, there's no reason why you can't bring curves tangent to a straight line in order to take out inside corners. So here's the rule. This is why. Once we understand that, we can come up with a workaround. We can re-engineer our process, called a relief cutting. Once again, folks, this is a simple example of how you might think about a process. You don't have to learn all of everything that goes into engineering a machine tool to make it deliver more interesting things, but you need to learn a little bit about why it behaves the way it does. You always need to ask, why is that rule there? Once you understand it, sometimes you can find what the alternative is to get the very thing you want out of the machine. I want to go back to the machine and demo some of this. Okay, folks, I'll try and demonstrate some of what I just scribbled on the board about to give you a sense of how relief cutting works. And again, this is an example of a thinking process about how to acquire something that's not immediately obvious out of the machine. So start off with, well, like I said, you like to draw on your material so you can get some verification as to what's going on. And this will tell me roughly how often to make my relief cuts. And we'll do, start off with some tangent cutting, some straight relief cutting, some inside corners. And then I'll do something that's a little bit of all of that. By the way, one of the byproducts of relief cutting can be small pieces like that. And so there is a tendency for a small piece of material to get pulled down into the table plate, and if that happens, obviously you can't proceed. There is a funny little place that our population that still likes to often visualize with a pencil on paper. A particular type of hole that our group of drawing folks can fall into. I'd be remiss not to mention here. And that is when you conceive of an idea, you sketch it out, you come down to the shop, you translate that sketch onto your material, and then you proceed to cut. Your brain can fall into drawing space. And when your pencil line goes somewhere you don't want it to go, typically you just grab an eraser, get rid of it so you can continue in your drawing, visualizing process. How that behavior manifests itself here, I've seen be like this with the machine running. Pretty scary. Real close to getting nipped by that saw blade. If you think you might have that vulnerability, keep an eraser on the table. Because it's just fine to do this with the machine running. It's not fine to do that. But even more important than its usefulness is it's a visual cue. Folks, it would suffice to say that no one has come to the University of Michigan to become career machine operators. This is usually a means to an end. It's not your first priority in life. And so that puts you and me and most of us who are artists and designers and so on at a higher elevation of risk when it comes to working with this stuff, because while we're working, we have the tendency to allow our minds to go off into design land. Oh man, if I can do that, I can do this. Next thing you know, your focus isn't at the point of purchase. Where's your fingertips? Where's the saw blade? It's wandering around in space, thinking about the next thing you're going to do. You, me, all of us in that kind of space need little compensating behaviors to help keep us on task and keep ourselves focused where we really need to be. Because creative folks tend to not easily turn off that creative side of your brain. And yet when you get to working on a machine tool, it's not that the creativity goes away, it's just you're doing that back at the bench. And then you make a decision, then you come to a machine and you work out that thing. And it's that kind of back and forth. You don't want to do those things simultaneously. And I don't care whether you're doing it for 5 minutes or 50 years. As a matter of fact, some of the worst accidents in here have been senior faculty and me. And in almost all cases, it's been your mind was wandering off to some other creative aspect of your project and not staying here where you are. You will see as you work where you have those vulnerabilities, create little behavior patterns to help you out. Straight relief cutting. You'll either get too many or not enough. If it's too many, you end up with that little bit of debris getting caught in the table plate problem. If it's not enough, you're going to hear it. You're going to hear that blade straining the way it did when I did this cut. And if that happened, you could simply back up and cut alongside your cut to make room to continue your curve. But notice I was rotating the material while I was pushing it forward. Hard inside corners. And if you need to draw that curve, draw it. So on and so forth. Simple relief cutting. Anytime you're doing a sculpted sort of project, you're going to find you're be combining all of those things. But the operative importance is that you're maintaining the space for that blade to deliver what you want it to do. And you'll know that you have to make that accommodation because you will have sketched on your material and you'll recognize that somehow or another you're exceeding the radial limit of that blade. Now you've seen me, or at least heard me, bringing that blade to a more rapid stop. I've been stepping on a brake pedal here. Folks, please, if you're going to use the brake, make sure the machine's turned off before you use that brake. And you don't have to brake all the time. Video time is costly time, so I'm not going to sit here and let the blade come to a stop by itself. But if you're done using the machine, you can turn it off, lower the guard, let it slow down by itself. You don't have to stand on the brakes. Brake shoes are expensive. These brake shoes cost more than automobile brake shoes, for crying out loud. And we've got lots of garbage cans, and it's often helpful to keep one near where you're working. Alrighty, there's a fundamental principle that applies to almost all stationary machine tools and an awful lot of hand power tools that you need to recognize. And the sooner you do, the safer you'll be, the more rapidly you'll adapt to what your role is in the operating process of the machine. And it's what I call resistance to the force. Applies to almost every machine tool, both stationary and hand tools. There'll be a direction or a multiplicity of directions that the thing doing the work delivers force. There'll be things designed into the tool to help resist that force. You need to recognize what those are and conform to them. And if you can't conform to them, then learn how to build jigs and fixtures that allow you to orient in a way that conducts that force back to the component of the machine that is supposed to resist it. Now, the bandsaw, which is one of the reasons we like to introduce folks to machine cutting of materials as a bandsaw, is because it is probably the most obvious and the easiest to understand. This blade is moving in a downward direction. The teeth are hooked down. There's a component of force going down. Guess what? The table is here to resist that force. If the table wasn't there, the material would just instantly be thrown to the floor. Now, if you understand that in the pit of your gut, you will never try to pick things up in space and cut. Oh boy, does that make a mess. Breaks the blade, often injures the user, trashes your material, all unnecessary. Now, you may think, but I want an angle like this. Well, guess what? We can actually set the angle of the table. And when you come in your class, I'll get into some of those finer points on the machine, but we can set the table at an angle. Okay, well, suppose that you can't get it that way. Can't get what you're after with the table set at an angle. So let's suppose that we wanted to hollow out an area and we had to go into the blade like this, and the table only tips right and left. It doesn't tip fore and aft. We'd have to find a way to convince the blade that we're doing this even when we're doing that. So we might build ourselves a little fixture. Jigs and fixtures. Jig is something you use one time, a fixture is something you use over and over and over again. So what's important about the fixture? It's important that it be very secure on the table. It's not going to be tippy. And there has to be enough room to throw a clamp on here. Holding this with your fingers isn't enough. So we'd get a couple of clamps on there. And then we could, let's say, make this kind of cut into the corner here. So we're resisting the force of that saw blade, but we're doing it in a responsible way. We're not just picking things up in space. And you're going to find when we get into talking about other machine tools, which we will undoubtedly be doing once you get assignments and we start working with other tools and other machines to satisfy that assignment, that every machine tool has a force delivery thing that you have to be conscious of. What does the machine do? What do you have to do? The more complex machines like table saws, they have at least 3 directions of force, of which the table only picks up 1. The operator has to pick up 2. That's why that saw is so dangerous. is the operator has a huge responsibility in operating that tool to make sure that number one, the operator doesn't get injured, but also doesn't injure anybody else, which is the biggest concern in a public shop like this. When we get to drill presses, not always that obvious. There's 3 directions of force there. It's not just down, and the table takes care of that, but it can also lift things up. It can also spin things around. And again, we'll address that stuff when you guys come in for your assignment seminars, the things that are specific to the project you're going to do this semester.